The verification of software programs involves proving that a program satisfies a formal specification of its behavior. Sub-areas of formal verification include deductive verification, abstract interpretation, automated theorem proving, type systems, and formal methods. In this video, we'll be discussing some examples for propositional logic and predicate logic. I am Dushani Pereira. Let's start off with the first question. It says that P and Q are propositions. P represents the election is decided, and Q represents the votes have been counted. So let's take those two down. P is the election is decided, while Q represents the votes have been counted. Part A asks us to write the compound proposition to represent the election is not yet decided. So if P represent that the election is decided, then the election is not decided will be given by negation P. Part B, the election is decided or the votes have been counted. So this means the election is decided is P, the votes have been counted is Q. So there's an O in between, which means we have to put the O sign. C, the votes have been counted, but the election is not yet decided. The votes are counted, Q is true, but the election is not yet decided. The election is not decided. The election is decided is P, so not decided is not P. Since both of these statements happen at the same time, we need to join them with an AND operation, which means the votes have been counted. At the same time, the election is not yet decided. Part D, if the votes are counted, then the election is decided. If the votes are counted, then the election is decided. So this is an if-then statement. So votes are counted is if this is so, then election will be decided. So it is if Q, then P. Now let's go to part G. The election is decided if and only if the votes have been counted. The election is decided is P, votes have been counted is Q. If and only if. This talks about a by implication, which means the implication happens both ways. So we have to use the by implication sign when we answer part G. Next, let's go to part H. Votes have not been counted. That's not Q. The next part is O. They have been counted, but the election is not decided. So let's look into the second part now, which is this part. They have been counted, but the election is not decided. So the second part says that they have been counted, but means at the same time of Q happening, election is not decided. So negation P, not P. Q and not P. And these two are joined with an O. So we have to use O in the middle. So I hope the first question is clear to you. Now let's move into the second question. Express the following using propositional variables and logical connectives. Let's look at part A. You can access the internet from campus only if you are a computer science major or you are not a freshman. So let's say your propositions are you can access internet is A. If you are a computer science major, let's say that is C, proposition C. And then if you're a freshman, let's name it F. So what this question says is you can access the internet. If you want to access the internet, then you need to be either a computer science major or not a freshman. So you need to be a computer science major or not a freshman. This is the answer to part A of question number 2. Let's look at part C of the same question. To use the wireless network in the airport, you must pay the daily fee unless you are a subscriber to the service. Express your answer in terms of W. So W is you can use the wireless network in the airport, and D means you have to pay the daily fee, and S means you're a subscriber to the service. Okay. So what the question says is to use the wireless network. If you want to use the wireless network, which is W, if you want to use it, then either you have to pay the daily fee or you have to be a subscriber to the service. So if you have to pay the daily fee, that means you're not a subscriber, which means the proposition is D. So you have to either pay or you have to be a subscriber. Subscriber is given by S. So this is how you write the answer to the part C. Now let's move into question number 3, where we have to draw path trees. Okay, let's look at part A. When we draw a path tree, we have to figure out separate parts of the formula. That helps us to draw the path tree without a question. So let's put brackets and separate sections of our formula. Alright, now as you can see, the implication comes first on top, and then on our left hand side we have an and. Towards the left hand side of the and, this is the and towards the left hand side of that and we have the negation sign, and after that we have P. So this is how the left hand side of the branch goes. And then towards the right hand side of this and sign we have Q, which is the atomic proposition. So the leaf nodes of this tree will always have atomic propositions. And then let's come to the right hand side of the implication. In the right hand side we first encounter the AND operation. Towards the left side of the AND we have P, and to the right we have an O. The left to O is Q, right is not R. This is how we draw the tree for the first part of the third question. Let's go to part B then. We have negation P implies Q. So we have the implication sign. Towards the left we have the not, Then we have P, the atomic proposition. Then we go to the right hand side, we have the implication. Left side is P, right side is Q. Right. Part 4 says find the properties of the following propositional expressions. So we have to express whether these formulas are satisfiable or falsifiable or valid or invalid. So let's first look at what these actually mean. If a formula is said to be a tautology, then that means all of its outcomes will be true, will be 1. There'll be no zeros. In that case, it's a tautology. In other words, it's valid. If a formula is said to be a contradiction, that means all of the outputs are zeros, are false. There's not a single case which will actually satisfy this particular formula. So that's the difference between being a tautology and being a contradiction. If it is a tautology, all the outputs are true. If it is a contradiction, then all the outputs are zero, false. Then, satisfiability. If a formula is called to be satisfiable, then that means there's at least one case which makes the formula true, which makes the formula 1. In that case, it is said to be a satisfiable formula. On the other hand, being falsifiable is there should be at least one case which makes this particular formula 0 or false. In that case, we say that this formula is falsifiable. There is a certain case or cases which will make the formula false. In that case, it's falsifiable. So if a formula is a tautology, then definitely it will be satisfiable as well. So for example, once we draw the truth table for a formula, if we get all ones to the output column, if all of the outputs are 1, then this is said to be a tautology, since everything is 1. Or else we call this being valid. That formula is a valid formula. If in case all of these outputs are zeros, then we call this formula a contradiction, where none of the outputs satisfy the formula. Then, if there's a case where at least one of these outputs are 0, then we call this a falsifiable formula, which means there's at least one case which makes our formula false. And finally, if there's a case where at least one of the results are true or 1, then we call this satisfiable, which means that there's at least one case that the formula will be proved to be true. So if the formula is a tautology, that means all the cases are 1, all the cases are true, then definitely that particular formula is satisfiable as well, because in all cases it's true. So it is satisfiable. I hope that's clear to you. Keeping that in mind, let's go to question number 4, part A. Part A is POQ or negation POR. Okay. POQ or negation POR. Alright, let's draw the truth table for this and see what we get. PQR negation P, POQ or negation POR. Alright, so we have 3 variables: true, 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 false, false, false. true, false, true, false, true, false, true, false. All right. So the equation would be 4 false signs and 4 true signs. So let's see what we get as the output. Since all of these signs are O signs, if at least one of the atomic propositions are true, then this entire thing would be true. So it will be easy for us to fill. The first one is P, so everywhere where there's a P, we can make it true. And for the other 4, there's a Q, these 2 are true in Q, so they are true as well. And then negation, no, in the third one, R is true. And then finally negation P is true, so this is true. So as you can see, all of our outputs, all the outputs are ones, which concludes this is a tautology. And at the same time, this will be valid since it's a tautology, and also since it's a tautology, we can conclude saying that this is satisfiable as well. Let's move into question number 6 now. Show that the premise is if you send me an email message, then I will finish writing the program. Okay, so this question is about prepositional logic. We need to come up with atomic prepositions for fractions of sentences. So let's go on with the question. Let's continue the question while taking down our prepositions, atomic prepositions. So I'll say, send me an email is P. So let's continue. Then I will finish writing the program. Okay. Finish writing the program. Let's call that Q and let's continue. If you do not send me an email message, then I will go to sleep early. That's a new premise. Go to sleep early. Let's call that R. Let's continue. And if I go to sleep early, then I will wake up feeling refreshed. Okay, that's a new premise again. Wake up refreshed. Let's call that S. Let's continue. Lead to the, okay, so premises are over. Now we have the conclusion. Lead to the conclusion. If I do not finish writing the program, then I will wake up feeling refreshed. All right. Now, first of all, let's construct our formulas. So the first part says, if you send me an email message, then I will finish writing the program. If you send me an email message, then I will finish writing the program. P implies Q. Next one. If you do not send me an email message, I will go to sleep early. I will go to sleep early. And then the last one is, if I go to sleep early, then I will wake up feeling refreshed. Yes. All right. And the conclusion says, if I do not finish writing the program, then I will wake up feeling refreshed. I will wake up feeling refreshed. Okay. So this is what I have to do. Let's see how we can construct this. This question is a bit confusing when you start off with obtaining the answer, the final answer. So you may pause the video and try writing the answer. It will be a bit confusing. Let's do it together. I'll start with the first premise, which is P implies Q. This is my premise. It has been given to me. In order to get the answer here, if you pause the video and try this question, then you might have encountered a bit of an issue here. So what I do in order to get the answer easily is I'm going to get the contrapositive of the first premise. Contrapositive means you get the negation of both sides in the same implication and connect them with the implication. So you swap the two atomic propositions and join them with the implication while making them the negation. So this is called the contrapositive. Contrapositive of premise 1. That's what we have done here. Then number 3, I'll again take my second premise. That's a premise. And now what I see is here you see its negation Q implies negation P, and here we have negation P implies R. So these two together should ring a bell in your head with regards to the rules of inference. So this is a hypothetical syllogism. So what you can do is I can discard negation P and directly take negation Q implies R, and this rule is hypothetical syllogism. Implication, we are introducing a new premise here, so we write I, and then the rules that we use to come up with this are 2 and 3. So 2, 3. This implication means that the symbol associated with this rule is implication, and this I is to say that we introduced a new premise. If we are discarding one, then we write E to represent elimination. If we are introducing, we write I. And then what we do is we take the next premise we have, R implies S. This is my next premise. And here I see I have negation Q implies R and R implies S. Again, this is hypothetical syllogism. So we discard R and we write Q, negation Q implies S. This is again implication I, 4 and 5. So when you write answers for these type of questions in the exam, you have to use these notations. These are the things which will be marked in the exam paper. Without writing the name of the rule, you have to write the notation. Okay, so we're done with the question. Now you see the answer we want is what we got. Okay, so at the first hand, this question would be quite confusing, but then when you try to do it with the contraposition, then it will be quite easy. Now let's look at question number 7. So it says, Randy works hard. So along with the question, let's take down our premises. Randy works hard. Let's give it a letter. Let's say it's P. If Randy works hard, then he is a dull boy. Okay, Randy is a dull boy. Is a dull boy is Q. If Randy is a dull boy, then he will not get the job. Randy will get the job. Let's say it's R. So the question says Randy will not get the job, but then I wrote the premise in the positive form as Randy will get the job. So usually when we write premises, what we try to do as much as possible is we try to come up with the positive version of the premise without going on with the negative version of it. So it's always good to use the positive version. Alright, now let's come up with our formulas. First we have Randy works hard, which is P, and then we have Randy works hard If Randy works hard, then he's a dull boy. If he works hard, then he's a dull boy. And then finally we have if he's a dull boy, if it's Q, then he will not get the job, which is negation R. And the conclusion, as the question mentions, is he will not get the job, negation R. All right. So let's first write our premise. And then we'll take down our second premise as well. P implies Q. This is my second premise. And then what I can do, again, with the use of rules of inference, is that I can use the rule modus ponens and I can isolate Q here. This is the rule of modus ponens. So how do I write the notation for it? This is implication again, and I'm eliminating, like I mentioned before, you're not introducing something new, you're eliminating P here. So this is E for elimination. And since we take the second atomic preposition here, what we do is we write E2. If it is P that we take, then it's E1. If it is the second that we take, we write E2. And what were the premises we used for this? 1 and 2. Okay, so I hope this is clear. And then number 4, let's take our next premise. This is my premise. And then 5. Okay, again, what we use is modus ponens, just like before. We will isolate the second, so implication, elimination, the second. 3, 4 were the premises we used. So I have the answer that I wanted. Now let's look at part C of question number 8. If it does not rain or if it is not foggy, then the sailing race will be held and the life-saving demonstration will go on. Okay, let's take down our premises. If it does not rain, okay, let's say it rains. That's P. Next we have it's foggy. That's Q. And then we have then the sailing race will be held. Sailing race is held. Will be held. Let's see, it's R. And the life-saving demonstration will go on. Life-saving demo goes on. Let's call that S. And then, if the sailing race is held, then the trophy will be awarded. If the sailing race is held, then a trophy will be awarded. Okay. The trophy will be awarded. Let's call that T. The trophy was not awarded. Is the conclusion? No, it's not the conclusion. It rained is the conclusion. Okay. Okay, let's take down our premises. If it does not rain, if it does not rain, or if it's not foggy, if it does not rain or if it's not foggy, then the life-saving demonstration will be held and the sailing race will be held. Okay, the life-saving demonstration and the sailing race. And the sailing race, both will be held. If the sailing race is held, then the trophy will be awarded. And finally, the trophy was not awarded. The conclusion is, it rained. Okay, so let's see what we can do. I'm first going to take our premise, second premise, R implies T. You can pause the video and try to solve the sum first, and then you can look at the answer. And there are several ways in which you can solve a sum as well, so you don't have to stick to the method that I use. You can do it in the method that you want. It just has to be correct. And then I'll next take my third premise, which is negation T. You see, I have R implies T and I have negation T, so this should again ring a bell. This is an inference rule. Well, I can use modus tollens here, and I can conclude negation R here. So this is modus tollens MT on 1 and 2. So now I have negation R. So now what I do is to get the answer that I finally want, what I'm going to do is I'm going to add a separate section to the result that I got in the third part. So addition doesn't make a difference because it's an OR. So only one part has to be true for an OR condition to be true. So I will add negation S to negation R. This doesn't make a difference because negation R is anyways true. It's a So adding negation S would not make a difference. So I'll write here addition. And then what I do is I'm going to use De Morgan's law on the fourth, and I'm going to take negation out, and I'm going to write R and S, which is using De Morgan's law. On 4. Okay, now I have this. And then I'm going to choose the first premise I have. This is a premise. As you can see, I have already created the right hand side of the premise in the sixth part in the fifth, in the negation form. So what I can do is I can easily use modus tollens here. So that's what I have been doing all this time. That was my thought process. I added negation S to negation R so that I can use De Morgan's law on it and come up with the negation of the right hand side of the first premise. So what I'm going to do now is I'm going to use modus tollens and get the negation of this. This is using modus tollens on 5 and 6. So usage of modus tollens gave me the negation of the left hand side of the implication in the sixth part. So now what I do is I again apply De Morgan's law and take the implication inside the bracket, and I simplify it to P and Q. This is De Morgan's, using De Morgan's on 7. And then finally what I do is, again, when you look at the 8th premise, you need to think about the inference rules. What should come into your head is simplification, the rule simplification, where you can take out one part of an AND operation, because if they are connected with an and if it is a premise, then both are true. So taking one out doesn't make it false. It'll still be true. So what I'm going to do is Since from these two what I want is P, I'm going to take P out, and my rule is simplification, but I'm not going to write simplification in English here. I'm going to use the notation. So what's the notation? Since this is this is and you're not introducing anything, you are eliminating something. So it is E. What did you take? It's the first, so it's E1. And what did you use to do this elimination, or in other words, the simplification? It was the eighth premise, so it was the eighth. And now you have the answer what you were looking for. Let's move to question number 10. Translate each of the following statements into logical expressions using predicates, quantifiers, and logical connectives. So all this time what we were discussing was prepositional logic, and now we're moving into predicate logic as the heading suggests. So here we have predicates. Cx denotes x is in the correct place. Cx says that x is in the correct place. And then Ex denotes that x is in excellent condition. And finally Tx suggests that x is a tool. Okay, so now what we have to do is we have to translate these English statements into logical expressions. So the first one is something is not in the correct place. Now this means that there exists something which is not in the correct place. So there exists, not for all. This is not a statement which is generally applicable for all. It's only applicable for some. So this is how you symbolize some as taught during the lecture. So there's some x which is not in the correct place. There's some tool which is not in the correct place. So there's some x which is not in the correct place. X is in the correct place is denoted by Cx. So if x is not in the correct place, then that's given by not Cx. So there's some tool which is not in the correct place. I hope that's clear. Part B. All tools are in the correct place and in excellent condition. This is a for all statement. All the tools, not just some tools, it's all the tools. So all the tools are in the correct place and are in excellent condition. So for all x, if this is a tool, x is a tool, if it's a tool, it is in condition, in excellent condition and in the correct place. So for all x, for everything, for all, if it's a tool, then it is in the correct place and it's in excellent condition. I hope that's clear. This says all tools are in the correct place. So for all tools, it talks about all the tools. So for all x, we need to say that it's a tool. If it is a tool, then it is in the correct place and in excellent condition. Part C, everything is in the correct place and in excellent condition. Now we don't have to mention that this is a tool or not because it's not mentioned in the statement. So we have to just say for all x, they are in the correct place and in excellent condition. That's it. Here we don't have to specify that it's a tool because that's not given in the statement itself. Part D. Nothing is in the correct place and in excellent condition. So nothing is in the correct place. There's not even one tool which is in the correct place. So for all x, nothing is in the correct place and in excellent condition. Now, if I don't put this not, this means that everything is in the correct place, and is in excellent condition. But when I put this not, this means that nothing is in the correct place or in the excellent condition. I hope that's clear to you. Now let's move into question number 13. Questions like question number 13 are quite common in FMSV and also in certain subjects that you will encounter in the second semester or the fourth year. So let's see how we can do it. So LXY suggests that X loves Y, where the domain for both X and Y consists of all people in the world. Use quantifiers to express each of the statements. Okay, part A. So the only thing that we have is LXY means X loves Y. Part A is everybody loves Jerry. So here we're talking about everyone in general. So this is for all X, and LXY is X loves Y. So if everyone loves Jerry, that means loves everyone. X means everyone for all X. X is everyone. X loves Jerry. So this means for all X, X loves Y. For everyone, everybody loves Jerry. B. Everybody loves somebody. So for everyone in general, there are certain people whom they love. For all X, there's some Y whom they love. For all X, there's some Y where X loves Y. Everybody loves somebody. Here you can't use the same variable in both cases because everybody and somebody are two different people. See, there's somebody whom everybody loves. So there's somebody whom everybody loves. So this is a bit tricky. There's a particular person whom everyone loves. So there's this just one person whom everyone is loving. So in this case, we have to first take some first. Some should come first. Some Y should come first. This particular Y should come first because he's just one person who's loved by everyone. There's some Y for all X where X loves Y. Whenever some is in front, whenever some Y or some X or whatever some is in front, that means there's just one person who is involved with regard to everybody else. Alright, part D. There's somebody whom Lydia does not love. So here, what happens is there's this particular person whom Lydia doesn't love. Here also we're talking about just one person, not everyone. So what we have here is we have one person and we have Lydia. Lydia doesn't love this person. So here also we have to take some in front. There's some person, there's somebody where you have Lydia, and Y. This Y is somebody whom Lydia does not love. So L means she loves. To make it a not, we have to put a not in front. So this means there is somebody whom Lydia does not love. Party. There's somebody whom no one loves. So again, this is just like C and D. There's somebody, some person, there's this particular person whom nobody loves. So there's one person for all X where no one actually loves him. So there's some Y for all X where nobody loves him. Part F. There's exactly one person whom everybody loves. So this is again a bit tricky. So what happens here is there's exactly one person, there's this particular person whom everyone else loves. So if we represent this in a graphical way, there's some person whom everyone, here you have all the other people, you have everyone else here, and you have this particular person here. Everyone loves this person. But you can't stop there in this question. You have to go further. You have to say that it's just one and only one person who's being loved by everybody else. So you have to say that if there's somebody else, if there is someone else, then that person is equal to this person. Because there cannot be two people whom everybody loves. There's just one person whom everyone loves. So you have to justify the fact that if there is a second person, then that person is also equal to the first one whom you initially talked about. So this is how we are going to construct our answer for part F. So let's see how we can do it. I hope the scenario is clear to you. So what we do is there's some person for everyone where X loves Y. And then you also have to say that if there is a second person, if there are any Z, now Y is the person whom every X loves. So if there is a Z, if by any chance there's a Z where X loves Z, then you have to say that Z is equal to Y. According to the diagram that we drew, that's what we are going to do. If X loves Z, that means that Z is equal to Y. There cannot be a second person. I hope this is clear to you. I shall draw the picture again so that you will better understand it. So there's one person over here whom all of the other people love. All of the other people love this person. That is what the question is, but you have to justify the fact that if there is a second person, then that person is equal to this first person whom you mentioned, because there cannot be two people whom everyone loves. So you have to also say that if by any chance, if there's a Z, then this Z is equal to this particular person whom you were talking about. All of these people are X's. And this one is a Y. You have to say that this second person who's a Z cannot exist. He has to be equal to Y. Let's look at part G. Everyone loves himself or herself. So this again is generalized for everyone. So for all X, loves X. Now it says that everyone loves him or herself. So everyone loves himself. So X loves X. For all X, X loves X. That means everyone loves himself, or it's she, then she loves herself. 19. Express each of the following statements using quantifiers, then form the negation of the statement so that no negation is to the left of the quantifier. Next, express the negation in simple English. Okay. So the first one is all dogs have fleas. So let's say dx denotes that x is a dog and fx denotes that x has fleas. So if we want to say that all dogs have fleas, how do we write this? This is generalized for all x, so this is for all x. If it's a dog, then it has fleas. This is how we write it. Now to take the negation of this, let's take the negation. To take the negation, let's first convert this into the form that we are used to. So I converted this implication to the format that we are used to. So if I am to remind you about it, P implies Q can be converted to negation P or Q. So this is what we used here. Alright. Now to get the negation, we have to give this entire statement a negation. So then how do we simplify this? Negation for all x becomes sum x. Then the negation goes inside the bracket. Negation dx or fx. Then you have for sum x, get this negation inside the main bracket. We have dx and negation fx. This is our final answer when we negate the statement. So you will see that this is satisfied now. No negation is left. No negation is to the left of a quantifier. So there's no negation towards the left of a quantifier. Now, when we take the negation here, we have a negation towards the left of this particular quantifier. But now we have taken the negation inside the bracket so that now there are no negations towards the left of a quantifier. Alright, now we have to write this in simple English. That's what's expected from the question. Now how do we write this in simple English? If all dogs have fleas, then how do we negate it? If all of the dogs in the world have fleas, as a counter argument, what we can say is there's at least one dog who doesn't have fleas. So that's how we negate it. So the answer to this in simple English is there is a dog, there is at least one dog who does not have fleas. That is interpreting the negated statement in simple English. I hope that's clear to you. And now let's go to part D. No monkey can speak French. Okay, let's say that mx represents that x is a monkey. So what I'm doing is I'm defining my predicates. Mx is x is a monkey. And let's say fx is x speaks French. All right. So no monkey can speak French. So no monkey means it's generalizing this for all the monkeys in the world. So for all x, if x is a monkey, then it cannot speak French. This is what the question says. For all x, if x is a monkey, then it cannot speak French. This negation symbol talks about the opposite of speaking French. That means it cannot speak in French. Okay, now let's get the negation of this entire statement. So before we do that, again, let's convert this into the normal method that we are comfortable with. O negation fx. So again, what we used here was this. Now, let's negate it. We need to get the negation of this entire statement. So now, let's simplify. Not all x is some x. Take the negation in. For some x. Now simplify the outer negation with the inner negations. Mx and fx. I hope the simplification is clear to you. Now, our initial statement was no monkey can speak French. So, to give it a counter argument, what we can say is that there is at least one monkey who can speak in French. If the statement is saying that nobody can do it, then what we have to say to do the opposite is we have to prove that there's at least somebody who can do it. So that's what we have done here. So now what we have is there's at least one monkey. There are some monkeys who can speak French. For some x, it's a monkey and it can speak in French. So to write this in simple English, we can say there is a monkey who can speak French. So I hope it's clear. For some x, it's a monkey and it can speak in French. That is the negation of our initial statement. This is the negation of this statement. Now let's look at the final question, which is part E. Part E says, there exists a pig that can swim and catch fish. Px says that x is a pig. Then Sx says that x can swim. And finally, we have Fx, which says that x can fish. Alright, now since we have these, what we can do is we can build our statement. So there is some x where x is a pig and it can swim. At the same time, it can fish. This is what our statement talks about. There exists a pig that can swim and catch fish. So it's a pig and it can swim and it can fish. Now let's take the negation. So to get the opposite of this statement, what we have to do is we have to put a not in front. Now let's take this not into the bracket. So not some becomes for all, and then we have our statement as it is. Now let's simplify. This is De Morgan's. Okay, now our initial statement was there exists a pig that can swim and catch fish. To make it clearer, I'll write this as an implication. For all x, px implies sx or fx. So this makes more sense. For all x, if it's a pig, it cannot swim, nor can it fish. So let's write this down in simple English. All pigs cannot either swim or catch fish. With that, we conclude this tutorial. I have left some questions for you to try. So that's it for this video, and I'll see you in the next tutorial.